In section 1, we're going to be looking at two different concepts, but these two concepts are going to lead us into the next section. So I want to kind of discuss and wave hands and talk about what's going on in this section, but really we're just setting ourselves up for section 2. So section 1 is instantaneous rate of change in tangent lines, or instant velocity. So let's just kind of start with an example and say, suppose we drop a tomato from the top of a 100-foot building and time its fall. And you can see we've got a little man here, and he's standing at the top of a 100-foot building, dropping that tomato, and then splat. And so after 0 seconds, it's just leaving our hand. 0.5 seconds, a little bit further, you can see it takes about 2.5 seconds to get there. So we've kind of got a picture, but also a graph from it, and then our table. And so there are some questions that are easy to answer directly from our table that we know about. It says, how long did it take for the tomato N to drop 100 feet? And so you can see right here that when we are at 0 height, we are at 2.5 seconds. And so how long did it take? It took 2.5 seconds. How far did the tomato fall during the first second? And so if we look at the distance, it went from 0 seconds to 1 second. That's during the first second. It was at 100 feet, and now it's at 84 feet. So we can say 100 minus 84, and that gives us that it fell 16 feet in that first second. How far did the tomato fall during the last second? Well, the last second would be between 1.5 and 2.5. There's the last second there. And so we went from a height of 64 to 0. And so we would say, okay, being a bit ridiculous, 64 minus 0. So that would be 64 feet. How far did the tomato fall between t equal to 0.5 and t equal to 1? So let's look at that information. Here's 0.5, and here is 1. And so we could see if we were to subtract those, that would give us 96, which is our 0.5, minus the 84. And so we get that it fell 12 feet. And so not super intense in these first few questions here. These are just a matter of looking at our table, seeing what the current height was, finding the seconds, finding information. But some more questions that might require a little bit more calculation would be part E. What was the average velocity of the tomato during its fall? Now the key word to this one is average. And so let's kind of talk about that concept there. If we're talking about the average velocity, okay, we're thinking about the average. We're thinking about the distance it has fallen over the total time. And so more in depth, that's the change in position. That delta is a sign for change over the change in time. Well, if you think to your algebra days, when you talk about the change in something over the other change in something, this is just slope. And so when I'm taking the average velocity, I'm trying to find the slope between those 2 points. And so if I think about was the average velocity during its fall, I know that we went down 100 feet, so negative 100 feet, over 2.5 seconds. Now I'm doing the negative here because this negative shows me the direction that it was going downward 100 feet. So it's dropping. And so this totals out to be equal to negative 40 feet per second. So the average velocity of the tomato during its fall is the negative 40 feet per second. What was the average velocity between t equal to 1 and t equal to 2? So we're going to have to come back up here to our chart. So let me just kind of, didn't mean to do that. Let me just kind of erase. Sorry about that. Let me just erase what we've already colored on here. And so now I want t equal to 1, and I want t equal to 2. And so I'm looking at these two values. So I'm looking at 84 feet and 36 feet. And so if I think about what we just did in that previous one, and I think about I am finding the change in position over the change in time, that means I'm going to have to do some calculations here. So at 2 seconds, so I went from 2 seconds minus my 1 second, and at 2 seconds we were at 36 feet minus our 84 feet. So doing some small subtraction there, that gives me negative 48 feet over 1 second. And so that tells me that the average velocity is negative 48 feet per second. So you can see our average overall the fall was negative 40 feet per second, but the average just between second 1 and 2 was negative 48 feet per second. And so you'll notice that when I'm looking at all that I'm doing here in these two questions, we are finding the average between 2 points. This goes back to your linear functions and your slope, your algebra days, things that you did in other courses. Now, some questions that are a little bit more difficult would be, how fast was the tomato falling 1 second after it dropped? And so when you look at this question and we're looking at 1 second after it dropped, you'll notice that this is a little bit different. We're looking at an instant in time. We're not looking at an average over the whole fall. We're not looking at an average over just, between t equal 1 and t equal to 2. We're looking at an instant in time. And so what this is going to be known as is this is going to be your instant velocity. We want the instant velocity, not an average. So we're going to have to approach this a little bit differently. You'll notice too that this is only at 1 point. So the previous two problems were the average over 2 points, and you can see just changing up our values, we got different averages depending on what we're looking at. We want the instant velocity at 1 point. And so our average over the fall was negative 40, but you'll notice that it was slower at the beginning, and then as we moved to that 1 to 2 second, it got faster at the end. So a better approximation is if we take those averages closer and closer and closer to that 1 second mark. And so let's kind of dive into that and see what we can do with it. And so what I want to do is just give us a little bit more room here. I want us to take and do some averages, but let's take it a little bit closer. And so let's first look at the average between 0.5 and 1 second, because our goal is to see the instant of what is happening at 1 second. So I'm going to look a little bit before it. And so if I do my calculations there between 0.5 and 1 second, I'm just going to go back up to my table and grab some data. That would be 84 minus 96 all over 1 minus 0.5. And I'm just pulling the seconds and the height from the table we already had. Doing my subtraction, this gives me negative 12 over 0.5. Then when you divide that, that gives you negative 24 feet per second. So the average between 0.5 and 1 is negative 24. So now let's look on the other side of 1. And so I want to find the average between 1 and 1.5 seconds. And so again, I'm going to do some small calculations. I'm going back up to the table previously. I'm going to grab some more data. So I'm going to say 64 minus 84 all over 1.5 minus 1.0. Do your subtracting here. 64 minus 84 gives you negative 20 over 0.5, which divides out to be negative 40 feet per second. So we could make an assumption here and say, so the instantaneous velocity at 1 second is between, so looking at a range here, is between 24 feet per second and 40 feet per second. And so you can see how this trend has begun to change of what we're looking at. Instead of taking an average over the whole fall or just a little bit, we were looking a little before it and we're moving kind of slow. We got that negative 24 feet per second. We go a little bit after our 1 second we're looking at. Now we're at negative 4. So we have an idea that between the 24 and 44 is going to be our instantaneous velocity. Now we're math people. We want to be a little bit more accurate than this. So let's kind of further dive into this into this conversation and this concept and see what we can do with it. So kind of some facts here I want to throw here before we move on into another definition. It says, in general, the shorter the time interval over which we calculate the average velocity, the better the average velocity will approximate the instantaneous velocity. Meaning, if I can get closer and closer and closer to the exact point that I'm wanting, so not just a half a second away, but maybe a quarter of a second or, a tenth of a second away, then what we're doing is the average velocity over time interval is the change in our position over change in time, which is the slope of your secant line through 2 points. The instantaneous velocity at a particular time and height is the slope of the tangent line at the point given by time and height. And so let's dive into that, because that's where we're going to really see the concept that we're moving closer and closer into. So here's a graph here, and this graph has just the curved line that is red, and it's working with our data from our table. So just taking the table from earlier with dropping the tomato and looking at the speeds. And so you can see that if I were to take the average from 0 to 2.5 seconds, it would be a secant line through those 2 points. And so we were trying to figure out what was going on at 1 second. And so if I look at the secant line between a half and 1, we get this one. If we look at the secant line between 1 and 1.5, we get this one. But our goal is to create a tangent line just going through that point at 1 second. And so to summarize this up, we have this nice yellow chart here, and it says the average velocity is equal to the change in position over the change in time, which is the slope of the secant line through 2 points. Your instantaneous velocity is going to be the slope of the tangent line to the graph. So as we're kind of working through these problems, let's consider these concepts and see how can we find that slope of the tangent graph? And that's going to kind of be the main point of this lecture. So lots of words just for dropping a tomato. And so you can see on this next part, I have a nice little graph here. Let me kind of move it up for us. And so if I'm looking at this graph here, and we've got our nice curve going on, and we've got some points, I want to find some information and see what's going on with it. And so the first part of information I want to do is I want to find the slope between 2 points. And the 2 points I want to find it between is the point 1, 2 right here. And so I'm going to use the point 1, 2. And I want to find it between the point 2, negative 1. And so if you go back to what you know about slope, this is y2 minus y1 over x2 minus x1. So here would be x1, y1, x2, y2. Just plugging into my slope formula, this gives me negative 1 minus 2 all over 2 minus 1. Finishing out your arithmetic there, that gives you negative 3 over 1, so just negative 3. And so my slope, if I were to create a line between these 2 points, would have a slope of negative 3. Furthermore, let's get closer to it. So what if I take the point, and I now look at the point 1, 2, so keeping our same point there, and I get a little bit closer to it, and I look at 1.5, So 1.5, comma 1. Okay, so I'm going to do my slope formula again. And so again, x1, y1, x2, y2, and I'm going to subtract this. So 1 minus 2 over 1.5 minus 1 gives me negative 1 over 0.5. So I get negative 2 for its slope. So if I connect these two dots, I get the secant line through these two, and my slope has now changed to negative 2. Now I'm going to keep on working through this, and so now I want to look at the slope between this point. I'm going to get a little bit closer here, and so I'm going to look at the point 1, 2, and I'm going to look at the point 1.3, 1.5. So I'm getting closer and closer to 1, and I'm hoping to get closer to this idea of a tangent where it's only going to touch the curve once. And so again, I'm taking my slope formula, so x1, y1, x2, y2, so that gives me 1.5 minus 2 all over 1.3 minus 1, ending up with negative 0.5 over 0.3. Using your calculator, this works out to be negative 5 over 3 if we just reduce that down. And so negative 1 2/3, and so if I connect these 2 points, this now gives me almost getting closer to that tangent line. So you can see what's happening with the slopes here. We have a slope of negative 3, we have a slope of negative 2, then we have a slope of negative 1 2/3. So the closer and closer to we get that point 1, we're slowly creating a flat line at the point 1, or known as a tangent line. So we began to see that as we draw these lines, we can make a best guess for what the tangent line would be, what measure would its slope be, and we can continue to see kind of a pattern that's going on with this. So you should have noticed that as this interval got smaller and smaller, the secant line got closer to the tangent line, and its slope got closer to the slope of the tangent line. So that's good news. We now know how to find the slope of a secant line. And we can kind of note too that in some applications, and I made this note here for your notes, we're going to do this a little bit more in a little bit, is that in some applications we need to know where the graph of a function has horizontal tangent lines. So again, pulling up some algebra here, we may have to find, went a little bit too far there, we may have to find where the slope is 0. And so we'll have to find those horizontal tangent lines. So I've got a small little example here underneath it. It says at the right, beneath it, is the graph of y equals g of x. At what values of x does the graph y equal g of x have a horizontal tangent line? So tangent line is defined as only crossing your function at one point. And so you can see, where would tangent lines be horizontal? It would be right here, right here, right here, right here, and it's just touching at that one point, whereas in previous ones we were looking at secant lines. And so this is just a matter of looking at your graph and pulling out some values. So this would be at the point x equal to negative 1, x equal to positive 1, 2.5, and 5. So some of the questions you're going to encounter, you're just going to be calculating your slope as you go. Some of them you're going to encounter and you're going to be creating maybe some secant lines as you go. And then some might just be analyzing some of your graphs. So before I move into some other examples, what I want to do is I want to switch over and I'm going to do a nice illustration talking about taking these secant lines and creating tangent lines. Here's a nice graph, and you can see here's this curve coming up here. And then if I take 2 points on this curve and create the slope between them, so I've just picked a point here and a point here, you can see it here is the secant line between those 2 points. Now what you notice in our last examples is that as we moved the outside point closer and closer to the other point, that our secant line slope is changing. And as it's getting closer and closer, you'll notice less and less change between it. You can even see here that between the 2 points, like it's kind of hard to distinguish the extra space between them, as we did way up here, where we're like, okay, when we move from this point to this point, we see some dramatic changes in slope, and we still see that we are crossing at 2 points. But again, as I get closer and closer and closer, you can see that this is becoming more and more like a tangent line. So as I move closer and closer and closer to it, you're seeing less of a dramatic change in the slope, which you can see these points are slowly come together, and then now we have that tangent line. So this is what we're talking about here. This is where we're taking this secant line and we are moving 2 points closer and closer till that distance gets smaller and smaller and smaller, and then we're able to actually see what's going on and create this tangent. Now, we are math people and we are lazy people. We like, variables to represent situations. We like to take paragraphs of problems and turn them into equations. And so this section is just leading us up to what we're going to do with this instantaneous velocity. But I want to give you a really good visual to show you what's going on as we're moving it closer and closer. So now that we looked at this tomato problem, we looked at secant lines and tangent lines. To wrap up this lecture, I just want to do a little bit of some of the examples and maybe some of the problems you'll see. You will be kind of using a calculator on some of this, and then other parts of it we're going to kind of do by hand. So here's the first one I will look at with you. It says, what is the slope of the line through 3, 9, and xy for y equal to x squared? And that's going to be our first question. And so here are my 2 points. I have the point 3, 9, and xy. And so you have to remember a little bit of previous knowledge. And so we already know that our slope is equal to y2 minus y1 over x2 minus x1. And so we're going to use that information down here. So this is going to be my x1, y1. This is going to be my x2, y2, or we're going to call them variables there of x and y. So that would be y minus 9 all over x minus 3. Now, we can't do much with that information, but they did tell us that y is equal to x squared. So I'm going to plug that in right here for this y. So it gives me x squared minus 9 all over x minus 3. Now, in the top function, we are able to factor that, and so that factors into the difference of 2 squares. So x plus 3, x minus 3, all over x minus 3. Now this cancels since I have multiplication on top and bottom of that x minus 3. And so this cleans up into x plus 3. And so although this has definitely upped our difficulty level compared to dropping a tomato, we now have kind of a formula for finding m, because that's what all that was for. And so if it says, what is it when x is 2.97, I've already kind of done all my legwork here. And so for 2.97, I'll say, okay, well, when x is equal to 2.97, that's going to be equal to 2.97 plus 3. So I get 5.97. And then it says, what is it for x equal to 3.001? Well, again, we've done all our legwork in the light blue writing there. So this is going to be 3.001. So that would be 3.001 plus 3. So I get 6.001. And so you can see slightly moving on the other side of 3. I'm slightly on the other side of 6. And again, we're just plugging in for this x here, these different x values they give us. So then they make it a little bit more generic and said, what if you were at 3 plus h? So basically we are looking at the point of 3, but we're just going slightly to the h of it. Now we didn't want to look at just 3 because you can see here, looking at just 3 causes division by 0, and we're going to look at that more in depth. So now if I look at 3 plus h, that's going to be equal to, again, plugging that in right here for x. So 3 plus h plus 3, so that's going to give me 6 plus h. And so I'm starting to get an idea of what's going on at that point, that it's looking like it's going to be at about 6 when x is getting near to 3. Now it says sketch a graph of that, and so if you know your parent functions, this is y equals x squared. And so if I'm here at 1, 2, 3, about here, and I were to draw a tangent, the slope of that line, because again, we are looking at slope, is going to be about 6 plus h. So that slope is going to be about positive 6. It just depends on how far away from 3 I was, or h away. And so it says the slope is going to be closer and closer and closer to 6. Last problem to wrap it up. It says the graph shows the distance of a car from a measuring position located on the edge of a straight road. What was the average velocity of the car from t equals 0 to t equal 30 seconds? So if we're looking for average velocity, you just want to think slope. So we want to look at t equals 0. And so that would be the point 0, 0, 0 for my seconds, 0 for my distance. And we want to look at 30, and that would be at 30 seconds, 300 feet. And so then if I just want to find the average between that, that would be coming down here, 300 minus 0, all over 30 minus 0, giving me 300 over 30. So that would give me about 10 feet per second. So the average from this point to this point would be 10 feet per second. Now part B says, what is the average velocity of the car from t equal to 10 to t equal to 30? So let's kind of remove what we did on that last graph. And so if I look at t equal 10, that would be right here. So that would mean that we're now at the point 10, 100. And then t equal to 30 would be right here. We've already grabbed that ordered pair, 30, 300. And so again, if we do slope, that would be 300 minus 100, or average velocity, 30 minus 10. That would give me 200 over 20. So again, that would give me 10 feet per second. So pretty interesting that between those two, we're still at 10 feet per second. Now in this next one, we're going to be looking at about how fast was the car traveling at 10 seconds, at 20 seconds, at 30 seconds. So we're going to have to do some guesstimations here. And so what I'm going to do is I'm going to kind of look at 10 seconds here. And I'm going to try and create some kind of tangent here that's just crossing at that one point. And so I kind of create a tangent of this one. And so at 10 seconds, we're at about 100. And then it kind of connects down here at 5 seconds being at 0. So doing that slope, we get a guess of about 20 feet per second. And we can see it's kind of a better incline there. At 20 seconds exactly, thinking about slope and tangents, it's just flat. That's a slope of 0. And so how fast are we going? We're going about 0 feet per second. So we're stalled out. Now, 30 seconds, if I just kind of create a tangent that's going on there, it looks something about this. And so kind of calculating that out, we're almost going at 100 feet per second. And so you can see these averages, although between 10 and 30, or even 0 and 30, looked about 10 feet per second. We were going a little bit faster at 10. We came to a stop at 20, and then we're going super fast at 30. What does the horizontal part of the graph between 15 and 20 seconds mean? And that's right here. Kind of need to erase my graph each time. And so this little flat part here. So that probably means that the car was not going forward, or it wasn't moving. So the car was not going forward. And that's just going to go back to, what does this graph represent? And what does slope represent? E, what does the negative velocity at 25 represent? And so you can see here at 25, the slope at this point looks like it's going downward. Now this is a graph that shows the distance of a car from a measuring position on the edge of a straight road. And so if that is going negative, then this probably means that the car is moving backwards, just by that negative slope, and that this graph represents the distance from a measuring position. So I hope this gives you an idea of what's going on in 2.1. As you're working through the homework, please feel free to reach out to me for any assistance.